So thanks for giving me this opportunity to talk with you. So what we know in BSM physics, which is the burning question, is this the question of dark matter and what is about its microphysics, mainly its connection to standard model particles. To address those questions, there are several class of experiments like direct detection experiments and indirect detection experiments. So in direct detection experiments, we can probe this DM nucleon cross section, whereas in indirect detection experiments, we can probe this thermally averaged annihilation cross section. So, but unfortunately, we do not have the positive result till now. But however, these compact objects like neutron star, which is mostly full of neutrons, can capture dark matter particles, and thereby we can probe dark matter parameter space via studying these neutron stars. So for this talk, I will assume this sigma v is 0. So that means we would be dealing with non-annihilating dark matter. So let me quickly summarize my talk. So and then I will go into the details. So the thing is that excessive dark matter captured in capture via this cross section sigma chi n. So so I have said the annihilation cross section is 0. Okay. So excessive dark matter capture can transmute this neutron star into a black hole. And now this black hole formation is heavily dependent on thermal states of dark matter inside the neutron star, in particular if this dark matter is bosonic. So now the next question would be that how can we probe these thermal states? How do you know that which thermal state produce black holes? So for that, the gravitational wave signals can be useful, and with a lot of data, maybe we can distinguish between these thermal states inside the neutron star. So let me go to this dark matter capture in the neutron star. So neutron star is a compact stellar object having mass around solar mass, and this is a very tiny radius. This is 10 kilometers. So it's a very compact object full of mostly degenerate neutrons. So now if a neutron star resides in a dark matter rich regions, it can pull the dark matter particles inside its core. But if there is no interactions, that means no dark matter neutron interaction, then this dark matter particles would come out of the neutron star. So we need tiny interactions. So, and how tiny? And you can see that it is 10 to the minus 45 centimeters square. Now you compare this cross section with Higgs production cross section in the LHC. So this is 10 to the minus 35. So little bit of interaction can accumulate dark matter. And this is the dark matter capture rate. So now that for neutron star transmuting to the black hole via this dark matter capture, we need that dark matter particles should be self-gravitating. That means that only happens when dark matter density is comparable to the neutron density in the neutron star. So now let's say we wait for 10 to the power 6 years, and we are assuming, let's say 1 GeV dark matter particles, and these dark matter particles, if dispersed over the entire volume of the neutron star, then its density is this 10 to the 21, whereas the neutron density is 10 to the 38. So that means even if I wait for entire age of the universe, then it cannot reach up to here. So what should then happen? So these dark matter particles, if thermalized within the neutron star, then these dark matter particles can be packed in a very small, tiny region, and then it can be self-gravitating. For example, if let's say again 1 GeV particles, and we wait 10 to the power 6 years, and if it can be confined within a centimeter, so then it even larger than the neutron density. So okay, so now how this thermalization happens? So this thermalization again happens for the same interaction. The interaction which is responsible for the capture, the same interaction would thermalize it. And this is the thermalization time scale. And you can see there is a dependence on dark matter mass for this thermalization time. This is because if the dark matter mass is less than the neutron mass, then all the neutrons cannot participate in the scattering process because neutrons are degenerate. So now, so if it is thermalized, then we can relate its dark matter kinetic energy to its potential energy. This potential energy is due to the neutrons. So then we can use the virial theorem and we can get this thermal radius. So as you can see here that if as the neutron star temperature decreases, this thermal radius also decreases. That means as the neutron star temperature decreases, we can pack the dark matter particles into smaller regions. And remember, the capture is also happening. So we would reach up to a certain point where the self-gravity of the dark matter cannot be negligible. So that number is this. When if the dark matter particle number inside the neutron star reaches up to 10 to the 49, then it becomes self-gravitating. Okay, so then the dark matter core collapse happen. So now, as we are talking about bosonic dark matter, it can also form Bose-Einstein condensate inside the neutron star. So if this happens, so then we need smaller number of particles to happen this to collapse this dark matter core, because in Bose-Einstein condensate the thermal pressure is negligible. The pressure is only coming from the 0 point energy, the quantum pressure. So, but we have to satisfy this condition. So now, as we can see that there are two possibilities. Black holes, this core collapse can happen from this non-BEC state and also can from this BEC state, but depends on this evolution of neutron star temperature and the dark matter parameters. So given these dark matter parameters and the temperature evolution of the neutron star, one can dynamically determine which state would occur inside the neutron star, BEC or non-BEC. So now, after this dark matter core collapse, inside the neutron star there are many black hole forms, but to form that we have to satisfy these conditions that we need thermalization of the captured dark matter particles, and if it is a BEC state we have to satisfy this condition, or if it is non-BEC then you have to satisfy this condition. And now these mini black holes can acquire more baryonic matter to grow, but if there is a Hawking radiation, this black hole evaporation is there, so then it can evaporate. So we have to satisfy all these four to eventually transmute this neutron star into a black hole with mass of this 1 to 2 solar mass. So, so now the question is that how can I, from this picture, the neutron star going to this black holes, so how I can constrain my dark matter parameter space. Now, if we see old neutron star, let's say like 10 to the power 10 years, then we can put an upper limit on the dark matter capture rate, and thereby we can put an upper limit on the sigma chi-n, that dark matter neutron cross section. And if there can be another way, so from gravitational wave signal, so if we can somehow, or in future we can discover this type of black holes. So we mostly know of this stellar mass black hole, which is a bit higher in mass, I think over 5 times the solar mass, but if we can find this kind of solar mass black holes from that gravitational signal, so we can also constrain the dark matter parameter space. But here I have constrained my parameter space from this old pulsar. So now you can see in the low dark matter mass regime, so this regime with surrounded by this blue line, here the BEC forms, and out of which in this region is excluded from the pulsar observation, because if the sigma chi is above this line, then we would not see that old pulsar like 10 to the power 10 years. and here the black hole forms out of non-BEC state. So this is a self-gravitating regime, and this appears in the higher dark matter regime. And this part where BEC forms but no black hole, so this part is unconstrained from neutron star observation because of the black hole evaporation. So black hole evaporates, so that's why this is unconstrained. So here we have to just rely on our traditional direct detection experiments. So now the question is that can we distinguish between non-BEC black hole and BEC black holes? So for that, we need to look at gravitational signals. So here are some time scales. This is implosion time scale. So as I have said, that first a mini black hole forms inside the neutron star. So and then it acquires more baryons. So there is some time duration to give out the entire neutron star by that mini black hole. So that time is called implosion time, and implosion time is sensitive to the initial mass of that mini black hole. So as you can see, for BEC and for non-BEC states, these numbers are different. So that's why the implosion time is different for BEC and non-BEC state. And the total collapse time, neutron star to this black hole formation, this is called collapse time, which is also different for BEC and non-BEC state. Now, so let's say if we have a population of binary neutron stars, if we can wait and before this binary neutron star merges, if this collapse time is smaller than its merging time, then some of these binary neutron star can form these binary solar mass black holes, and the relative fraction of this binary neutron star and the solar mass binary black holes is sensitive to the collapse time. So with lots of statistics coming in upcoming years, we hope that we can distinguish between these two scenarios, given the fact we do indeed find these solar mass black holes in future. So this is the takeaway, that excessive acquisition of dark matter inside the neutron star can lead to destruction of the star. And for bosonic, thermal states are important in deciding black hole formation. And we can use this old neutron star to constrain the dark matter parameter space. But to distinguish between BEC and non-BEC black holes, we need gravitational wave signals. So that's it. Thank you very much.
Questions?
How they will create the relic in the early universe?
Sorry?
How did you create the relic if the cross-section is 0?
So this is a non-annihilating dark matter. So one of the candidates is, let's say, asymmetric dark matter, where there is no annihilation, but it can form from that asymmetry created in the early universe. But for this work, we are not bothering ourselves with the early universe cosmology. So that's it. So this graph generated assuming 10 to the power 10 years old neutron star, this one.
There's a fair number of those, right?
Sorry?
Well, okay. So I guess what I should clarify is, so you want old, isolated neutron stars.
Yes.
Which are, so that would rule out the 350 or so millisecond pulsars, because those are really old.
Yes.
And would probably easily satisfy your.
So I need a very dense dark matter region and very old neutron star to constrain the parameter space here. The older the neutron star, denser the dark matter region, we would get a stronger constraint on this sigma chi-n.
Does it matter for you if the star is in a binary? Because, as I said, millisecond pulsars tend to be recycled And
Yes, binary pulsar also can constrain this, right?
Okay, so then maybe you can also take a look at pulsars which are, since you're looking for higher dark matter density, but maybe millisecond pulsars which are closer to the galactic center, as you were saying before. I'm guessing. But the other question I had is, we have this very, very recent result of a intermediate black hole candidate in one of the globular clusters from neutron star observations. And I was wondering if that is something that would fit your models, because it does produce 2.4.
So what is the mass then? I don't know that.
So the mass of this is just above 2. It's currently 2.2, 2.4.
Okay.
But the error bar is...
Okay, I would look into it.
Yeah, the paper is Keen et al. You might be interested in that one. Okay. But the other thing I was curious is, you also need gravitational waves. Oh, sorry. You said you need neutron stars of solar mass. Then
sorry?
Somewhere towards the end of your talk, you said you need neutron stars of solar mass, and that confused me a little bit.
So solar mass means this is 1 to 2 solar mass. So that's the range of the neutron star, I think.
Okay. So, yes. I mean, for me, all pulsars are 1 and between 1 and 2. Even pulsars we.
So this is a kind of just a rough estimate.
Okay.
Yeah.
So you don't need like pulsars sitting on 1 solar mass.
Yeah. No.
Oh, okay.
No, not that.
Hello. I have a question related to old neutron stars. So because of this capture, there is a heating that can happen. And for the older star, there is a cooling mechanism, like as it evolves. So there must be some bounds that the old neutron star that we have observed.
So heating, you are saying heating due to dark matter.
Yes.
So here I have put this annihilation cross section to be 0. So in most of the scenarios, people consider if dark matter annihilate to certain standard model particles which are confined inside the neutron star, then it can heat up the soup. So then you would get some late time heating can be probed by James Webb telescope and so on. So here I have, we do not consider this annihilation to happen. So we are not assuming extra heating for dark matter. So it's just a standard evolution, standard this Murka processes and photon cooling and so on.
Okay.
Okay.
You can have kinetic heating, just kinetic energy being deposited because you're accelerated with the field.
So,
but it produces much smaller temperature. But we can discuss later.
Okay.
If there are no more further questions, let's thank Deep again.